Today we'll be having a look at hydrogen bonding. If you haven't already, please check out the dipole-dipole bonding, which will give you a bit of context for hydrogen bonding. Let's get stuck into it. Let's have a look and try and explain how the hydrogen bonding works. Let's have a look at a very popular molecule that can exhibit hydrogen bonding, and that is hydrogen fluoride. We'll also think about water afterwards. Now, how does hydrogen bonding work? Well, we recall that fluorine is a very electronegative element, right? It's a very electronegative. And what does that mean? It really loves electrons. So there's going to be electrons hanging out inside this covalent bond, but the fluorine really has a strong pull on them, right? The hydrogen has a really weak pull, but the fluorine's pull is way, way, way stronger. So what's going to happen is that these electrons are going to get pulled towards that of fluorine. Now, if you have an excess of electrons, well, what happens? If you have extra negativity, that makes you negative, of course. And the hydrogen, because it lost electrons, it's going to be positive. When you lose negativity in your life, you become positive. Now, if you have a second hydrogen fluoride, chilling, well then what might happen? Well, we can see what might happen here. If I change the colors, I have blue and purple. The purple hydrogen is positive and the blue fluorine is negative. Again, this is between different molecules, right? This is one molecule and this is another molecule. You can see that this is distinctly happening between two different molecules. Because we have this is positive, this is negative, we even know that positive and negative attract, just like how north and south attract. So we can put in a bond like this. And what is this called? Well, that is our hydrogen bond. And that's it. This is the basics of our hydrogen bonding. If you have watched the dipole-dipole bonding video, you would have noticed that my explanation was almost identical, but for a different molecule. This is also the exact way that I explained this dipole-dipole bonding. And that's because these two are very, very related. Hydrogen bonding and dipole-dipole bonding are not too different. So then what is the difference? Well, the difference is that hydrogen bonding is very, very particular. Let me explain. Hydrogen bonding can only occur, so it's very, very picky, can't occur with any old molecule, can only occur if and only if, which we sometimes write as IFF. If and only if we have a hydrogen fluorine bond, a hydrogen nitrogen bond, or a hydrogen oxygen bond. If and only if there are these three bonds, can there be a hydrogen bond. We can see that here we have a hydrogen fluoride bond, so it's okay. This can have a hydrogen bond. You might say, well, why does it have to be with HF, H, and HO? Well, it's because these three substances are the most electronegative substances that exist, period, on our periodic table. These are the three most electronegative substances. So why does that make it special? Well, remember that electronegativity is how hard you pull. So if fluorine is so electronegative, right? If it's so good at pulling away electrons, what happens is that as compared to, maybe for a dipole-dipole, you pull it like a little bit like that, right? But for a hydrogen bond, you can pull it much more. You can pull it like way closer to you. So you can actually imagine maybe I have delta negative negative and delta positive positive, just to emphasize that it's actually, maybe doubly as strong as with a dipole-dipole bond. And so because it's the charge separation is doubly as big, then you can imagine that the force is going to be doubly as strong, right? In fact, we can definitely see this if we think about Coulomb's law, which is something in physics. So if you haven't seen this before, it's okay. Basically, this is a formula to determine the strength of attraction between two charges. So the F is the force, K is the constant, Q is one of the charges, so you can be like here, and that's the other charge. So you can see that if we make both of these charges a bigger number, we're going to have a much stronger force. Just like how if you have two stronger magnets, you're going to have more force between them. Okay, let's have a go at some questions to make sure that we're feeling comfortable with hydrogen bonding. Can this molecule undergo hydrogen bonding? No, it can't undergo hydrogen bonding. It might be very tempting because you can see hydrogens, and you can see fluorines. But remember, what do we say? If and only if there's a hydrogen-fluorine bond, not just if they're present. We do not have a single hydrogen-fluorine bond in here, do we? That means that this can't undergo hydrogen bonding. Can it undergo just dipole-dipole bonding? Absolutely. Why can it do that? Because the fluorine, it can still grab electrons from the carbon. The electron's going to pop over, and the carbon's going to be partially positive. Now, is this a dipole? Yes, it is. Is the charge separation going to be as big as with our hydrogen bonding? No. This is just a very small separation. You can imagine this is a very weak magnet. So even though it can attract another one, we're working with very, very, very weak magnets here. So the kind of forces that we're dealing with is much less than with hydrogen bonding. Because that's one of the things that really makes hydrogen bonding special, is that it's very strong. Hydrogen bonding is much stronger, about I believe 5 or 6 to 10 times stronger than with a dipole-dipole, depending on which dipole-dipole you're considering. Let's look at another example. Let's have a look at this question. Which of these dotted lines is a hydrogen bond? Only one of these answers is correct. So is this green one a hydrogen bond? Is it purple one, red one, or brown one? Which of these is the hydrogen bond? The answer is red, B. Let's walk through why the other answers are wrong. This can actually be really intimidating because a lot of them, well, actually all of them are between oxygens and hydrogens. And so now it is very confusing here. But don't worry. So what can we see here? Well, first of all, let's ask ourselves, can a hydrogen bond actually occur here? Do we have a hydrogen fluorine, hydrogen oxygen, or a hydrogen nitrogen bond? Absolutely, we have a hydrogen oxygen bond. We have quite a few actually. That's good. So definitely we can have hydrogen bonding occurring. Now let's try and see where they might be. Now the thing that makes me a lot easier to understand this kind of diagram is if I actually put on the positive and negative charges. So this oxygen here, it's going to be taking electrons away from the hydrogen. So I'm going to put a delta negative here and a delta positive on the hydrogen. Similarly, delta negative on this oxygen, delta plus on this hydrogen. How about this hydrogen here? Is it going to have a charge? Well, no, because the carbon-hydrogen bond is very neutral. So this is actually 0. There is no charge here. Okay, and same with this one and this one. Now we're ready to tackle this question. Let's start with this green one. The green one's going to be wrong for 2 reasons. First of all, if you have a look at this black molecule, that is the outline of the black molecule, the green force is intramolecular. Intra meaning within. Intramolecular. It is within the same molecule. That's definitely wrong. That is definitely not a hydrogen bond. Another reason why it's wrong is that this is a neutral atom trying to attract a partially negative atom. That is not possible. You cannot have, wood is not magnetic. A north pole is never going to stick to wood, right? So this is definitely wrong. Let's consider the orange one now. Again, this is going to be a hydrogen bond between this partially negative oxygen and this hydrogen, but again, it's still going to be wrong because this one has no charge. So But again, wood and magnet never stick, right? Wrong. How about this brown one? Same problem. Oxygen, partially negative, but this one's neutral. No stick. Wood, magnet, no stick, right? How about this one? Partially negative, partially positive. Well, that would work, right? Because it's like a north magnet, south magnet. They do stick, and that's why it's red. Let's have a look at another question. Which one of these is a hydrogen bond? There's actually two answers. It's going to be the red one and the purple one. Let's understand why. So first of all, let's try and eliminate some of the wrong answers. This brown one is wrong. And it can be a bit confusing. Why is the brown one wrong? Well, have a think about this, right? Hydrogen bonding is, again, fundamentally intermolecular, right? Remember, it is an intermolecular force. It is a force that exists between molecules. And this is definitely within the same molecule. So this brown one can't be correct. Another way that and something that can confuse the students is that they say, Bob, but didn't you just say that hydrogen bonding occurs when you have OH bonds? So here is what we need to understand. This oxygen-hydrogen bond is important because it creates the electronegativity difference, which sets up the ability for the hydrogen bonding, right? And then what's confusing is that, okay, now we have another kind of pseudo intermolecular bond between another oxygen and a hydrogen, but this is between molecules, right? This is really confusing, right? So see how this oxygen-hydrogen bond is within the molecule. It's not actually causing the hydrogen bond. It is simply the important material, the precursor to allow for the real hydrogen bond, which we can see here in red. That is the hydrogen bond. But this brown one, that's just an intramolecular bond. It's a covalent bond. That's all it is. It's definitely not this one. Let's have a look at the other options. Let me grab my black pen again. This is going to be partially positive, partially negative. Do positive and positive things attract? Do north and north poles attract? They absolutely do not. Can't be grey. Do negative and negative things attract? Absolutely not. South and south poles don't attract. Can a north pole attract a south pole? Absolutely. Can a north pole attract a second south pole? Absolutely. So that means that purple and red are both hydrogen bonds. Let's have a look at this question. Can this molecule undergo hydrogen bonding? And if so, which of these are the correct diagrams to show the hydrogen bond it's forming? So first of all, if we want to know if it forms hydrogen bonds, we have to look for, again, OH, NH, and FH bonds. Do we have those? Yeah, we can see a few OH bonds. That means that these two molecules are capable of forming hydrogen bonds. Okay, now that we understand that, now that we are sure that hydrogen bonds can actually exist, there's a lot here. It's a bit tricky, but trust me, it's not too hard once you just go through it methodically and we draw on those delta negatives and delta positives. So we have this oxygen here, it's going to be delta negative, and this hydrogen here is going to be delta positive. Same thing here, delta negative, delta positive, delta negative, delta positive, because of the electronegativities. All of these hydrogens are going to be neutral. Because they're not in a polar bond, there's not a big electronegativity difference. Let's have a think about here. This hydrogen and this hydrogen, this pink bond, is that going to be a hydrogen bond? No, because this green hydrogen is neutral and this one is neutral. Do non-magnetic things, does wood stick to wood magnetically? No, that's a bit ridiculous, right? Does this one attract this one? No, wood doesn't stick to a south pole. Again, this is intramolecular, so we instantly know it's wrong. But they're also both neutral, so that's also wrong. Wood does not stick to wood. Again, this one's also going to be wrong because it's south pole, and south pole of a magnet with wood doesn't work. Let's have a look at this one. the blue one between these two positive hydrogens. Again, positive, positive, that's not okay. Okay, so we've eliminated all of them besides the grey one and the light blue one. Let's see if these two work. So the grey one is between a partially negative and a partially positive. South and north poles still attract, so that's good. How about the light blue one, between a partially negative and a partially positive? That works. So those are the hydrogen bonds here. Again, the hydrogen, this here, so again, just to make sure, this here is not a hydrogen bond. That is just a normal covalent bond. We do not give a special name to that. That is not a hydrogen bond. Hydrogen bonds are always between molecules, and they are caused by OH, FH, and NH bonds. I hope you guys enjoyed, and I'll see you guys in the next one when we'll be discussing dispersion forces. See you then. We offer physics, chemistry, and math tutoring. For more insightful explanations like this one, head to tutorgum.com.